Hi! In this video you will learn to deal with negative cycles in the graphs. You will learn to detect whether there is a negative cycle in the graph and to find a negative cycle if you know there is one. And you will use that in the next video to achieve infinite arbitrage. But before that, you really need to learn to detect negative cycles in the graphs. And this lemma will help you. So it says basically that there is a negative weight cycle in the graph if and only if you make one additional iteration of relaxation in the Bellman-Ford's algorithm and some edge is relaxed. First, let's prove that if there is some change in the last step of Bellman-Ford's algorithm, then there is a negative cycle. Assume, for the sake of contradiction, that there are no negative cycles. Then it means that all shortest paths from S to any node in the graph contain at most v-1 edges. We've already discussed that. If they contain at least v edges, then there is a cycle, and this cycle is non-negative, so it can be removed, and the path will be either improved or just stay shortest path. So, no dist value can actually be updated on iteration number v, because we already found the optimal shortest path length with paths that contain at most v-1 edges, and we cannot improve anything after that. So this is a contradiction with the fact that the last iteration actually relaxes some edge, and so if it does, then there is a negative cycle in the graph. Now let's prove in another side that if there is a negative weight cycle, then there will be a relaxation on the iteration number v. Suppose, again for the sake of contradiction, that there is a negative weight cycle, for example a cycle of length 3, a, b, c, a, but there are no relaxations on the iteration number v. Now let's look at the following three inequalities. These inequalities basically state that edges AB, BC and CA cannot be relaxed on the vth iteration. But if we sum these inequalities, on the left side we will have sum of dist values for A, B and C, and on the right part we will have sum of dist values of A, B and C plus sum of weights of the edges of the cycle. And from this sum of inequalities it follows that the sum of the weights of edges is non-negative. But we know that the cycle is a negative weight cycle, so this is a contradiction. And so we proved by contradiction that there will be some relaxation on iteration number v. So we proved our lemma, and now we know how to detect negative weight cycles in the graph. We just do one additional iteration of Bellman-Ford's algorithm, and it doesn't increase its asymptotic complexity, its running time. And now we can determine whether the graph is good or bad, whether it contains negative cycles or not. Now we want not only to detect whether there is a negative cycle or not, also want to find some negative cycle itself, at least one. Maybe there are many of them, but we want some negative cycle. So first we still need to run exactly v iterations of Bellman-Ford relaxation. And as we know, if there is negative cycle, then for some node v, it will be relaxed. Its dist value will be decreased on the last iteration. So save this node, and I state that this node is definitely reachable from a negative cycle, because if it was not reachable from the negative cycle, then any shortest path to this node will contain at most v-1 edge, and it won't be improved on the iteration number v. So it is reachable from a negative cycle, and also it is reachable from a negative cycle with at most v steps, because if you have a shortest path from S to v, which contains negative cycle inside, even if there are more than v edges from this negative weight cycle to v, then there is another cycle on this shortest path, and it also has to be negative, because otherwise we can remove it from the shortest path. So v is definitely reachable from a negative cycle with at most v steps. And we remember the previous node from which each node was updated last time. we store it in the pref values. So if we go by pref links from v, and we do that at least v times, we will be already definitely on this negative weight cycle, because we will already return to the cycle by at most v steps, and then we'll just go around this cycle for some amount of iteration. So if we go by v times back, we will be on the negative cycle. And then the only thing we need to do is just to save the position where we started, and then go once around the cycle until we come to the same node, and we will know that the nodes we saw during this round trip are the nodes of the negative cycle. So this is the algorithm, and it works in the time of Bellman-Ford's algorithm plus proportional to the number of nodes. So basically the same running time as Bellman-Ford algorithm. So now the question is, again, if you have a negative cycle in your graph of minus logarithms, does it mean that it is always possible to get as many rubles as you want from $1,000? And unfortunately, that's not always the case. For example, in this graph, there is a negative cycle between euro, British pounds, and Norwegian crowns. And you can check that if you multiply the conversion rates on the edges of this triangle, you will get more than 1, and it means that for 1 euro you can get more than 1 euro. And this means in turn that you can get infinite arbitrage if you just make trades along the edges of this triangle for as many times as you want. But there is no possibility in this particular example to exchange euros for dollars. So you cannot exchange rubles for euros, then make many loops around this negative weight cycle, and then exchange euros to dollars. So this is not sufficient, and you cannot actually get any dollars from rubles. You cannot get any rubles from dollars in this particular case. And in the next video, you will learn how to determine whether it is possible to have an infinite arbitrage from rubles to dollars or from any other currency to any other currency, and not only to detect that, but to actually find a way to implement it if it's possible.